Thank you everyone for coming in this rainy weather. Luckily, we have Sharut today to share with us his recent research on redefining context for powerful test adaptation using unlabeled data. So a little bit about Sharut, maybe you know her as well. She's a third-year PhD candidate, advised by Professor Stephanie Yegoka, and her research interests focus on multimodal replication, robustness, and auto distribution generalization. And let's welcome Sharut.
So, thank you for the kind intro, Yife, and thank you so much for coming despite the terrible weather. I'm Sharut. I'm in my third year at MIT, and I work with Professor Stephanie Yegelka. And today's talk is going to be about how do you redefine context for powerful test time adaptation using unlabeled data. And I'll cover all these key text blocks here in the next couple of slides. Cool. So to set the stage, foundation models have shown standout success in a range of downstream tasks, be it from text to video generation, where we have OpenAI's Sora model, or DALI 3, which is a text to image generation model, or Dino V2, which is a self-supervised learning image model. With these foundation models, there has also been a change in the way we train a standard, typical like machine learning pipeline. So what we do now is we get large amount of multimodal unlabeled data from a range of domains. For example, in this case, could be images, text, sensors, speech, and so on. And then we train a large model on top, could be billions or trillions of parameters. And then this pre-trained model is adapted to your downstream task on a range of, and it's like tested on a range of tasks. And these tasks could be question answering, object detection, object segmentation, sentiment analysis, and so on. So now what are the ways that we can adapt a pre-trained model to our downstream tasks? So the first is actually zero-shot transfer, where we just take this pre-trained model and test it on whatever queries we have for your downstream task. But there's a challenge. The data we pre-train on is typically very different from the data we test on or the task that we have at downstream task. So the pre-trained model is actually not able to perform as well on these downstream tasks. So apart from zero-shot transfer, another approach to counteract this is fine-tuning, where you take this pre-trained model and fine-tune it on your task of interest. But there are a bunch of challenges with this setting. So the first is that your downstream data typically belongs to a niche task where you have very few labeled set of data points. And fine-tuning such a large model on such few data points can lead to overfitting. The second is that this is very resource intensive because your pre-trained model is of the size of billions and trillions of parameters. Although like more recently, there has been an exciting direction of research where low rank adapters are being developed to fine-tune these large models. And the third, which is the most important, is performance degradation and catastrophic forgetting. So it has been shown that if you fine-tune a pre-trained model on a specific task, then it loses out the properties that the original pre-trained model had and specific and like personalizes a lot on your specific task of interest. So this means that whatever new task that you have as your downstream task, you'll have to train a new model for it and like a specific model for it. So third type of adaptation technique, which has recently gained a lot of promise, is test time compute. Test time compute is that you enable your pre-trained model at test time with extra compute and extra time before coming to the final answer. And this has been shown to be a very powerful tool. And to motivate it a bit more, OpenAI's O1 preview model showed a lot of promise compared to its previous model, which was GPT-4o. There were huge gains in reasoning tasks like mathematics and code. And what was even more interesting was this new scaling curve at inference, which measures your accuracy with your test time compute on your x-axis. And it is shown that your performance actually monotonically improves with more compute you have at inference. And another very recent paper also shows that if you have a smaller model, a 10 billion small model, but you test it with test time compute, it performs better than a 14 times larger model, but with standard inference. So clearly this test time compute seems to be a very powerful platform to improve and align your models to a downstream task. So what are the existing approaches in this setting? So the first approach is in context learning, which was studied in back in like 2021 and gained a lot of promise and a lot of success after that. So what in context learning is that you have a given downstream task of interest, you sample a few labeled demonstrations from that task, and you prompt your pre-trained LLM at inference with those demonstrations. So as an example, on the first side, we have a simple translation task from English to German. And just showing model these XY pairs of your downstream task of interest, the model actually adapts to this task and is able to perform well on a new query, which in this case is chair. And these tasks vary across like a lot of domains. It could be taking a pre-trained language model and testing it on addition, multiplication, and so on. The second type of popular approach for test time scaling is this very recent paper again from Google, which is about search algorithms, where at test time you allow the model to do a Monte Carlo tree search and search across different range of preferences and before like coming to the final answer. And there are different ways you can do this search. For example, beam search, where you take top n preferences at each step and then move forward. Or look ahead search, which is another sort of preference-based search, where at each step you also take a look ahead reward and based on that decide which potential options to explore. However, across both these settings, there are like two key challenges. The first is that in context learning actually relies on ground truth labels to actually adapt to your new task. And the second with search algorithms is that their performance depends a lot on accurate reward models for these downstream tasks. So this means that to actually scale your test time compute, your task may face this data crisis that we don't have enough data with supervision, which is also something that image benchmarks hit back in like 2017 and 2018, when like people started studying self-supervised learning because the label data actually hit a wall. So how do you scale test time? How do you scale this test time compute and test time adaptation without any supervision? So that is what's the goal of this talk. That is how far we can go without like test time supervision. So given a new unsupervised task at test time, the question we try to answer in this setting is what all are the features of the downstream task that we can actually adapt to and how can we adapt to? And this is very important to train machines that mimic more and more like how humans learn, which is humans can self-explore and adapt to a range of tasks and a range of like out of distribution scenarios merely based on like a few demonstrations. And similarly, if you want to train a generalist robot, it's important that the robot can adapt to different environments and settings that it didn't see before without like retraining it each time. So in this talk, we are going to study this idea of using an unsupervised task at test time in two different domains. The first is, can you use this unsupervised task and unlabeled data from this unsupervised task to adapt your model to varying distribution shifts? And the second is, how can you use this unsupervised task to adapt your model to task-specific inductive priors? And I'll explain what each of each of the terms mean when I come to like that particular part of the presentation. So let's begin with the first half, which is about using this unlabeled data to adapt your model to varying data distributions. So distribution shift is everywhere, be it the task of self-driving cars, healthcare, code completion, and so on. So typically the data that you train on, it's rarely the case that it matches the distributions that you test your model on. And I'll be using this example of self-driving cars throughout this part of the presentation. So in this example, in this particular figure, for example, you train your autonomous vehicle on roads which have like sunny backgrounds or like grassy backgrounds, but at test time, your weather condition completely changes and you want to deploy your model on rainy backgrounds. And the harsh truth is that machine learning models exhibit huge decrease in performance when tested on such out of distribution scenarios. To study this robustness of machine learning models, we will particularly focus on the setting of domain generalization. So what domain generalization assumes that at training, you have access to different domains or environments. And when I say a domain or an environment, I mean data which is generated from a particular intervention on the data generating graph. So for example, in this case, again, coming back to the self-driving cars, you have data of like collected from different cities, different backgrounds, and so on. And mathematically, this can be denoted, your data set can be denoted as the collection of these tuples containing your current data point, your corresponding label, and environment index, which tells you which environment that data actually came from. and you have a set of training environments, and then at test time, you have a collection of completely new domains and environments that you have no access to at training. So this is also one key distinction between domain generalization and domain adaptation. In domain adaptation, you do have access to unlabeled data from your test time, but in domain generalization, you don't, and you literally just need to take your pre-trained model and deploy it in a new setting. And what makes this task very challenging is that because you don't have access to these test environments, you still need to train a model that minimizes the worst case risk and generalizes well. So in this setting of domain generalization, the bitter lesson so far is a simple empirical risk minimizer, or an ERM, works well when tested across a range of benchmarks in the wild. So what an ERM model does is that it collects all this data from different domains, pulls it all together, and directly just trains a predictor on top. So it doesn't care which image came from which data or which environment, and doesn't care about environment level features or distributional features, and just dilutes all the information that any environment has to give us. And the way it does is just minimizing the risk across all the environments, weighted by the sampling probability of the data from each environment. So where are we going wrong in this whole problem of addressing robustness of machine learning models? And to understand that, let's think about what all are the features that each environment can give us, which we can actually leverage to improve the prediction. And to understand that, let's focus it from the lens of unlabeled data. So at test time, you have unlabeled data from a new domain, and you want to just make predictions on them. And the goal is to make as better predictions as you can. So can this unlabeled data actually improve your prediction on a given sample at test time? So to understand that, let's consider this motivating example. Say you had training data from one user, and these are the training digits on the left, and you train a simple neural network on top. Now you need to deploy this on a new user at test time. Say this is the data point from the new user. And as you can see in the training data, the user makes 2 with the loops, which is shown here. And since this new data point also looks like a 2 with the loop, the model using the inductive biases of the training data will actually predict it as a 2. However, what if we collect more data from this user? There we go. And we see that this user actually makes 2 without the loops. So the correct prediction for this user would have been an A, but the model predicted it as a 2. So just unlabeled data from this user guides us about what are the characteristics of this user, and this is like a free untapped potential, which is just available to us, and we can use it for free at test time to improve our predictor. So this particular motivation has been analyzed in some previous works, and all of the previous works actually for this particular setting come under this heading of marginal transfer learning, or MTL. And let's see how this works. So say you sample a batch of data, all coming from a given environment, and your environment label is E, and you have K data points. What you do is you take a featureizer phi, typically like a CNN or a small neural network. Then you featureize each of the sample independently to get some feature embeddings. And then on top of this, you train a specific classifier which takes as input this average of the embedding vector and also your current input to make the corresponding prediction. So this average of embedding of your batch of data is what is called a context vector, and it is typically concatenated with your current input to actually make the prediction. And there are a bunch of papers which also come into under this setting of marginal transfer learning. There could be entropy minimization at test time, or batch norm alignment, and pseudo labeling, and so on. So what is the challenge with marginal transfer learning? Is this the optimal way to actually extract environment signals? And in this paper, we actually claim that it's not. And before going into the theory, let me give you a bit of insight. So assume that your current input that you want to make prediction on is an image of a cow. And say your context here, K is equal to 10,000. That is, you are using a batch of 10,000 samples to actually to define your context vector. And assume that in this batch of 10,000, there was only one image of a cow and all the other images were those of a camel. So if you just average out the embeddings of all these features, you will dilute out the signal that one single image of cow has to give you, which is very useful for your current prediction. So that is the key insight behind what's written on the right, which is that these models actually struggle when you need to find extreme level statistics, which is like finding a needle in the haystack. So as an example, if you want to train such a model, to implement this indicator function, which simply measures that how many images or like how many data points were bigger than the current data point, whatever came in the context. We show that your output dimension of the featureizer phi has to actually grow in your context length C to be able to implement such ideas. So this is a very good method to capture your distributional characteristics, but when it comes to such extreme level statistics, this model actually suffers. And I think I've given like enough background about foundation models and like why these approaches are bad, that you might be thinking like what's the correct way to actually use this unlabeled data. And most of you might have already guessed this, and the idea is very simple. What you do is you sample at training environment E, and you sample a batch of data from that environment. You just make it into a sequence, which we call as context, and you pass it through a transformer with causal attention. And you make the prediction of whatever task you have at hand directly at each context length. So if it's like a classification task, you directly predict the label corresponding to each of the image in this context. And the way you train this model is by simply minimizing this loss, where you randomly sample a training data point, so it's like expectation over all the training environments, and you minimize the error of this prediction at each of the context length. And the beauty of this approach is that for such an example that we saw in the previous slide, that is for needle in the haystack kind of arguments, because attention is so powerful, it can identify the right query which the model has to focus on to improve its predictions. And for that particular example of the indicator function, we can show that just a one-layer transformer with linear attention and sufficiently high temperature can achieve this target. Yeah, so that's a method, and it's a very simple approach, just using a causal transformer. And how it relates to this paradigm of in-context learning is a very small difference, that in your context, you now don't use any labels. So your context just contains a set of unlabeled data, and you make the prediction corresponding to each of the x's. And the reason we do this is that at test time, now on a new domain, you don't really have access to the labels corresponding to that task. And yeah, there was a question. So if you actually write down the loss of this term, if whatever like your logits are, you can, similar to like contrastive learning, you can divide it by a temperature constant while sampling, and you can show that it can do it in like just one layer. Yeah. No, similar to that, yes. Yeah. Yeah, there's like a very short proof. It's also in the paper. Yeah. But like in general, I feel the idea is these extreme level statistics can be modeled very well with attention. Yeah. Okay. Coming back. Yeah. So this is the method which we call as in-context risk minimizer, and it's very similar to that of in-context learning. Although the approach is very simple, it has really good and very interesting theoretical properties that I come to now. So I'll talk about 3 different theorems which analyze this particular setting. And to understand all 3 of them, let's just focus on this figure on the right, which measures what is the test accuracy of a given environment with respect to the context length. That is the number of samples that the model actually sees at test time. And we have 2 different baselines here. One is the global ERM that we already like discussed a few slides ago, which just pulls all the data together from all the environments and just learns a predictor. And then the second one is the locally optimal ERM of that environment. And what I mean by that is, if you just had data from that specific environment and you just train a model on top, it has all the information of that particular environment. So it's like the upper bound that we want to achieve. So the first theorem is zoom out, and we call it zoom out because we talk about its performance in the absence of any context. So the first theorem says that ICRM will behave as the global empirical risk minimizer across the support of all the training environments. That is at 0 context. This is ICRM's performance will be same as that of the global ERM. And an insight about that is ICRM is also is actually trying to learn a Bayesian optimal predictor of this test environment at each of the context length. And when you set context length to 0, it'll map ERM, which is also the Bayes predictor at 0 context length. The second theorem deals with a zoom in result. That is, if you have infinite context from that particular environment, can ICRM actually map your locally optimal ERM of that environment? And that's what this theorem is all about. So under some assumptions on your graphical model of your data generating process, we can actually show that at infinite context, ICRM's performance will be the same as that of your locally optimal ERM. So it achieves the same entropy. So the conditional entropy of your prediction given your current image and infinite context will be the same as the entropy of prediction given your current input and all the information that you have about that environment, which is represented by the capital letter E. So now we come to the theorem 3, which actually deals with the setting, which is in between no context and infinite context. So this is the partial zoom in. That is, if you have a partial finite context, can you claim anything about ICRM's performance? So under some more assumptions on the graphical model, which goes as that X and E are actually statistical dependent and they form the Markov blanket of the label Y, we can actually show that ICRM's performance is strictly monotonic with context length. That is, even at test time, if you have just one extra sample and you need to make a prediction for both, you can use that extra unlabeled data to actually improve your prediction on each of your data point. And that is what all the three theorems talk about with respect to this curve. And we can also test this empirically. And first, I'll show you like a proof of concept on a bit of a toy data set, which is this extended version of MNIST, also called FE-MNIST. So here, apart from handwritten digits, you also have lowercase and uppercase characters. And you have the metadata of which user wrote which character. So each user is like a training environment. Each user serves as an environment or a domain. So to give you an idea about the complexity of the task, at training you have around 300 environments, and at test time you have 200 new users that we had no idea about at training. And here we are looking on the right at the worst group test accuracy with the number of in-context learning samples. And I'm comparing 4 different methods here. The first is ERM, which is the global ERM we talked about, which just dilutes out all the information that a given environment has to give you. Then we have ICRM, which is our method of in-context risk minimization. Then we have 2 other methods of marginal transfer learning. One is TENT, which minimizes the entropy at test time. And the other is ARM, which is this method that we saw, which just averages the embedding of all the context samples that you have. So even on worst group accuracy, we can see that ICRM kind of follows the curve that we observed from our theoretical results. So at 0 context length, ICRM's performance kind of agrees with all these methods. And as the context length improves, ICRM is able to has a performance which is superior than all these methods. And it is able to do that just by 50 samples at test time. So extending these results to a bit more realistic setting, which is about tiny ImageNet C, where corresponding to a given image, you have data of corruptions and different type of corruptions and different severity of corruptions. And one particular type and severity corresponds to one particular environment. And in this case, we again observe the worst group test accuracy against the number of in-context samples. But something very interesting is happening in this curve, which is that although as your context length improves, your performance of ICRM is increasing, but there is something very interesting at 0 shot. So at 0 context, that is at no context, your ICRM's performance is much, much higher than all these other baselines. And the improvement with context is actually very less. So I don't have like a very rigorous theoretical result on this, but in the paper we show a simple setting of linear regression where we can provably show that ICRM's performance at 0 context will be better than that of ERM. But the insight is that using context at training allows your model to train a better featureizer, which can be used to have like superior performance even at 0 shot. And what I mean by that is typically in these data sets, there are a lot of spurious correlations. For example, we also test on Wild's chameleon, where color is a huge problem of spurious correlations. But we tested in the paper as well that somehow with this kind of training where we use context, ICRM is able to get rid of those spurious correlations and learn a better predictor. And that's also the reason why we see such high gains at 0 shot. Yeah, so there are some more results in the paper corresponding to like a bunch of other real world data sets. So feel free to refer to that. Lastly, can we understand how ICRM is improving its predictions? So we tested out on like a simple bunch of queries from a range of data sets. On the top, we have a given query from the federated extended MNIST data, and on the bottom, we have it from the ImageNet dataset. And on the top, we are observing like green bars on top of images. They indicate images that the model actually paid high attention to. The blue bar indicates the position of your current query in your context, and the red bar indicates the queries with low attention. From the top row, we can observe that the model actually attends to other images which contain curvatures, that is, these double curvature figures. And from the bottom row, on the left query, we have a person playing volleyball. And on the right, we observe its attention corresponding to the given context. And we can see that the model actually learns this semantic understanding of what a person looks like, because it pays high attention to this person also playing volleyball, and to this other image which contains people in academic gowns. Although there's also a false negative of a beach wagon, but overall, like, this gives us an understanding that your model is able to use your context as a source of like data augmentation, because now your model can use these augmentations of your input image and pay attention to them and improve its predictions. And it also has a semantic understanding of what the objects also look like. Yeah, so that's all about the method. And some key takeaways from this whole idea is that there is this duality between what context is in context learning and what an environment is in the setting of domain generalization. So if folks who are doing like robustness studies, if they treat their environment as context, then they can use these emergent phenomena from large language models and improve the robustness of their method. And folks in LLMs, pre-training, and so on, if they model their context as an environment, they can better structure their data to actually extract better capabilities out of these large language models or pre-trained foundational models. And in this half of the talk, we saw that how unlabeled data at test time can help you improve your featurizer and improve predictions. And ICRM is one such example where it can train to focus on the right amount of environmental features and improve its predictions. This is also in line with this famous quote by Leon Boutou, which says that nature does not shuffle data. Typically, like the way we train machine learning models is that we shuffle the data so that it doesn't overfit to specific characteristics of the data, and then we train the models. But with ICRM, whatever data is collected from the nature, you can literally take it in the same sequence, in the same temporal order, and just learn to continuously adapt to like different environments and different settings. Yeah. So although this is like a very interesting method to adapt to like different distribution shifts, but there was one key assumption that we made at the beginning of this talk, which was that we have the labels present at training. We were minimizing the risk at each of the context length for a given environment. But we know that we can't really scale having pre-trained, we can't really scale having labels at training. So what if there are no labels at training? That is when we enter this regime of representation learning, where we have humongous amount of unlabeled data. A typical pipeline in representation learning looks as follows. You have this huge amount of unlabeled data. You train a feature like extractor on top, and map your unlabeled data to a representation space. Then on top of this representation space, you have small scale adapters or like linear layers, which adapt your representation to your downstream task of interest. So for this part of the talk, let's look at, for example, these two downstream tasks. So what if we have a task of home loan approval or like credit loan approval? So we want the decision of this representation to actually be invariant to gender. However, if there's a doctor who needs to recommend some medicine to a patient, we want the prediction or the decision to actually be sensitive to gender, because the medicines actually depend a lot on the physiological characteristics of a person. Talking a bit more about some computer vision tasks, what if you're doing classification? Then your labels in the current input, they do not change even if you flip the image. But what if your downstream task of interest is segmentation? Then your segmentation mask also flips with flipping the image. So how do you learn this general representation which contains these task-specific priors, and how can you adapt them to these task-specific priors at hand? So that brings us to the second part of the talk, where we understand and see how can unlabeled data at test time help us adapt to these task-specific inductive priors. And I'll be mostly dealing with specific symmetries where I'll be talking about invariance, which is not being sensitive to, versus equivariance, which is being sensitive to in like loose terms. But the method is actually very general and can be applied to a range of like predefined features and specific latent attributes that the model actually needs to learn to improve the prediction. Yeah. So talking about this setting of vision, where self-supervised learning approaches can be broadly classified into two major categories. The first is approaches which enforce invariance, and the second are the set of approaches which enforce equivariance. So typically the way these models are trained is you have an unlabeled data right here. You apply a set of augmentations on top, which could be cropping, blurring, flipping, and so on, and you get a transformed image. And you train your encoder F so that it learns to map these two images very close together in the embedding space. And that's why it learns like invariance to these features or to these augmentations. And as we saw in the previous slide, what if your downstream task is classification versus segmentation? If this augmentation is actually flipping, then your representation won't be general enough to adapt to these two tasks. And to counteract that, there's this second set of approaches which instead learn equivariance, where they want that the embeddings of these two models are supported by a predictable transformation in the embedding space, which is denoted by TA. However, considering that this world is full of these contradictory symmetries, we can't enforce one of the two scenarios, because depending on this downstream task, we might need equivariance or we might need invariance. So we'll study here like how can we learn a general representation instead. So let's first see how these self-supervised learning approaches actually enforce invariance and equivariance through architectures. So the way they typically work is for invariance, let xk plus 1 denote your current image. A is your action or the augmentation that you apply on your current image, and yk plus 1 is your transformed image. Then you train your encoder F, which is like this blue figure here, and you get the representation of each of the two images. And then you just have an alignment objective to align these two embeddings together. And that's why they enforce invariance, because they don't use any information about A. And classically, the architectures that come under this setting are like Simclair, Moco, or like joint, and they're all like clubbed under this setting of joint embedding architectures or JEPAs. And for equivariance, there's a very simple change, which is that they use these parameters of the augmentation and now train a predictor which takes as input both your embedding of your current image and the augmentation parameters and try to align the output with the embedding of your target image. And because it uses all the augmentation parameters, it is sensitive or equivariant to these augmentation parameters. And although like mathematically equivariance is learning this predictable transformation in the embedding space, most of these works loosely deal with equivariance by studying this entropy, which is the conditional entropy of predicting your augmentation parameters given your embedding. This is treated as like a proxy measure of how sensitive or insensitive your augmentation or your representation is to your given augmentations. So as seen, these approaches, although they impose a good prior, which is useful for some specific task, they're very limited to generalize to a diverse scenario. So what we do here is a simple extension of this equivariance to actually learn selective equivariance and selective invariance. And to give you an insight, let's look at the same figure again. And let's say you have an input image and you transform it with a composition of a bunch of transformations. You can think of it as cropping on top of flipping and grayscale and so on. Now, we saw that if you want to enforce invariance, you just don't pass the parameters of this augmentation. And you instead just align the embedding of your current input with the embedding of your transformed input, which can also be written as this composition applied on top of xk. And we saw that to enforce equivariance, all you need to do is also pass the parameters of the augmentations that you want to enforce sensitivity to. So a simple extension on top is, what if you want equivariance to a subset of these transformations, say AI, but want invariance to all others? So what you can instead do is just pass the parameters of the augmentation you want equivariance to and not pass the parameters of the augmentations that you want invariance to. And this idea can be extended in the form of context. And this is our like key proposal, which we call Context SSL or Contextualized Self-Supervised Learning. So for a motivating example, let's consider two different symmetry groups in our pre-training, say color jitter, and the second is flipping. What you do is, For each of these augmentation groups, we create a certain context. And let's see how we do that. Say we are in the environment or a domain of flipping. What we'll do is, corresponding to each image, we have this transformed image, which we get after applying a range or a composition of transformations. But what we do is we use the augmentation parameters only of the augmentation corresponding to flipping, which in this case is denoted by these R's in like different dimension. Similarly, if you're talking about color, although your images in the context remain the same, the augmentation parameters that you now use are corresponding to the color jitter and not corresponding to the flipping. So this way you create a context which is now a collection of a current image, some augmentation parameters which indicate which environment or which group you're talking about, and finally your transformed image. Now, how do we use this collection of tuples to actually train our model? And the idea is again very related to how we did it in the previous half of the talk, except that now we have tuples of data. So what we do is, corresponding to a current image, an action, and your transformed image, we use the other images and all these other tuples as context. We take the embedding of your current image, your augmentation parameters, and your transformed image, and we just pass all of them together through a causal transformer again with attention. So the idea is that now this transformer with attention can look at all the past and try to figure out which group we are talking about, which is also enforced by these augmentations A. And finally, after taking the embeddings from this transformer, we just align these two together. So I like to emphasize that just by using this causal transformer with attention and this idea of using paired data for context, we can allow dynamic adaptation to task-specific symmetries. And before this work, all the other works in the domain of self-supervised learning actually either enforce invariance or equivariance. And this is the first work which can allow you dynamically change based only on test time without any retraining. And this is also very efficient because a transformer can produce the predictions for all the images or all the data points in the context in just one forward pass. And let's see how we train this model. It's through this very simple loss where we take expectation over all the symmetry groups in the data and an expectation over all the contexts that we can create corresponding to that symmetry group. And we just have this alignment objective, which is a simple extension of the Sinclair or inference loss, where you align the embeddings of xi and ai, which is your input image and your augmentation, with the embedding of yi. But the extension is that now you're conditioning on the context. So depending on what context you have, your alignment objective actually changes. However, there is a very surprising caveat that we have if we merely train the model with this contrastive loss. And to understand that, we'll see that just training your model with this paradigm actually induces a lot of shortcuts. And the first shortcut is, say this was your context, you had xi and ai and yi pairs. The first shortcut is that because you process yi after you take the embedding of ai, that is, your yi actually has access to xi and ai, it can just copy those embeddings over instead of actually learning what is the semantic content in the image. Because we are trying to align these two things together, the model can just copy the embeddings of what it learned for xi and ai and use the same for yi. So we use a very simple solution to actually deal with this. And what we do is, corresponding to each yi, we actually mask out the corresponding previous positive pair. So we mask out xi and ai, which is shown in this simple figure. Because our attention is also causal, so each of the token actually can't attend to the future. And there's this pair mask that we use, where corresponding to every yi, we mask out the previous input. We have another shortcut in this setting, which is a bit more non-trivial. And the idea is that because we use this contrastive loss in our case, we are also trying to separate out the positives from the negatives, that we want to distinguish between them and align them as far away possible in the embedding space. So since we are using attention, we are also using the tokens in the form of a sequence. And corresponding to each image or each positive pair, all the images are like negatives. And because of that, each negative and positive pair actually sees different contexts. So your model can actually use some simple shortcuts like just averaging the embedding of whatever it saw to produce like the embeddings to separate out the positives and the negatives, which is a shortcut, again, like preventing it from learning the semantic content. And what we do to address this is, again, another simple solution, which is just apply a random mask on top of each other. So on top of like the previous pair mask. So what it helps you to do is that now there are some positives and the negatives in your sequence which actually have the same context. And now to distinguish them, the model is forced to actually focus on the features which are actually relevant. So this is about the shortcuts. Now coming to a proof of concept of how this method works. So we first tested on this benchmark called 3D-IE bench, which is an extension of the ShapeNet data, and it contains 3D objects with different lightings and different poses. And we also have the metadata of what is the pose and what is the lighting condition of each image. And there are two symmetry groups in this case. One is color and the other is rotation. And we'll observe the performance of this method Context SSL under two different prediction accuracies. First is the rotation prediction and the second is color prediction. As we discussed a few slides ago, we use this proxy entropy method of predicting the augmentation parameters, and how well the model is able to predict the augmentation parameters is a measure of how equivariant or invariant the method is. So let's first look at the color context. So at test time, just by giving the model this new context of color, we can see that the model's rotation prediction accuracy goes down, but its color prediction performance actually goes up, showing that the model becomes more and more insensitive to rotation or more and more invariant to rotation, but more equivariant to color. Similarly, under the rotation context, we observe that the rotation prediction accuracy improves with the context length, but the color prediction accuracy goes down, showing that the model is becoming more equivariant to rotation, but invariant to color. And under this setting, let's also compare how Context SSL performs with respect to other existing baselines in the space. Let's first talk about the invariant methods. In this case, we have Sinclair and Vicreg, and we observe their performance on rotation prediction and color prediction. And as you can see, they have very low performance on each of those two tasks. Let's look at some equivariant measures now. We have three different equivariant baselines, and note that these baselines are specifically trained so that your representation is equivariant to rotation. However, Context SSL is this general representation which just uses rotation context at test time. And we are measuring rotation prediction accuracy, which in this case we expect to be higher because we are talking about the rotation environment, and color prediction accuracy, which we expect to be lower. And as you can see, Context SSL is able to do that and better compared to even specific methods that are just designed to be equivariant to rotation. We observe similar results for the case of color, where now in color environment, we expect the color prediction accuracy to go up, but the rotation prediction accuracy to go down. An important thing to note here is that Equimod, for instance, under the two settings, correspond to two different models. One which is trained equivariant to color and the other which is trained equivariant to rotation. However, Context SSL in these two rows are actually correspond to just the same model, but with different context at test time. So this idea of Context SSL actually extends to more realistic settings where you don't have these synthetic transformations. And to show that, we conduct experiments on Mimic3, which is a clinical physiological data set containing patient data admitted to a hospital. And we have two different tasks, one that measures fairness, which benefits from your representation being invariant, and the second which measures treatment prediction accuracy, which benefits from sensitivity to gender. And let's look at the performance of Context SSL under two different contexts. So first we have an equivariant context. We observe here that your invariance or like your fairness metrics actually worsen out with increasing context length, showing that your model becomes more and more sensitive to gender and hence showing poor performance on the fairness metrics. However, your equivariant task, which is treatment prediction accuracy, it actually improves with your context length. Similarly, now if you go to the invariant setting, we see that our fairness metrics actually improve with the context length. However, the treatment prediction accuracy goes down because your representation now is more insensitive or more invariant to gender. So this was all about the two methods that I wanted to discuss. Now coming to a quick recap and a bigger picture of what all we learned in this talk. So some of you might already know this, but very recently, just a few days ago, Ilya Sutskever gave this statement saying that scaling up retraining has actually plateaued, and this age we are in is an age of discovery where we need to find out what is the right thing that needs to be scaled up. And test time adaptation seems to have shown promise given the huge success of O1 model compared to its previous predecessor, which is GPT-4o. And in this talk, we saw that merely test time adaptation or test time compute is not enough, because if you want to scale it further, you actually have to see how you can adapt at test time without any supervision. And we saw that with respect to two different settings. One is adapting to distribution shifts, and the other is adapting to task-specific priors. In both the setting, we saw how you can use this idea of in-context learning, or how you can use context to model your representation and steer them in a particular direction. In the first, we just use unlabeled data independently, while in the second, we use this pair data to actually find out what are the inductive priors. This whole theme of test time adaptation, and specifically like Context SSL, is very related to this idea of world modeling, which is a very exciting and a popular direction for generative AI, video processing like video game engines, and robotics. So if you consider your current image as your current state, and your transformation as your action, then your transformed image as your next state, then your context serves as a trajectory or a history of whatever the model has seen in the past. And this way, your transformer actually learns a world model which tries to capture that given a current state and action, what would be the next state. And this is reminiscent of this fundamental idea of world modeling, which was first introduced by this paper back in 2018 by Schmidt-Huber, which says that as humans, we don't really learn the specifics of the environment, but actually focus on the abstract representations, which help us perform better at test time. So I'll leave you all with this thought, which is to actually improve your test time adaptation, you need to build better training paradigms which actually enable better test time adaptation. So we need to think more about how do we change the training to enable your model like learn these specific features at test time. And this has a lot of promise for specific tasks like reasoning, planning, interacting, and so on. So thanks to the wonderful team who was responsible for these two works, both at MIT and at FAIR. And these are the two works that I actually covered in this talk. And now, thank you so much for your attention. If there are any questions, I can take them up. Yeah. Yeah.
I'm curious. So with more testing, of course, naturally more technical inference, is there a way to balance that such that you get the accuracy benefits from more test training, but at the same time you can optimize inference step?
Yeah, I think there's, actually there's, let me show this figure. Okay. Yeah, so we don't really know for sure where this curve is going to take us. It might be possible that it actually doesn't scale monotonically higher after you actually increase the test time beyond a certain threshold. It actually goes down. So there might be a sweet spot, but it's still to a lot of, I think, effort and research directions to see how much you can actually scale at test time and what are like how is the balance between how more expensive you are at test time versus how much performance gains you're actually getting. Yeah. 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 Thank you. If there are no more questions, then thank you so much for coming. Yeah, thank you.
You're adding so much new slides.
Yeah. Okay, let's see. I think it's. I'll just leave the.
Story.